one is part of one of the
Okay, so we are very glad to have the Professor Brian Metzger from Columbia University. So as everybody knows, one of the biggest news in the 2017 was the detection of the gravitational wave from neutron star mergers. And this is a milestone for the mass messenger astrophysics astronomy, because not only gravitational waves, but also the gamma rays, X-rays, optical, infrared, and radio waves are detected. And then, in particular, the optical counterpart was the so-called kilonova emission. And then Brian has a major contribution to the modeling of the kilonova emissions. And then, indeed, surprisingly, the observed kilonova emission is quite consistent with what Brian predicted in the 2010s. And then Brian actually contributed the work on the wide range of the high-energy astrophysics, not only the underparts of the gravitational waves, but also the gamma ray bursts and supernovae and the novae and the other shock physics and several topics. So he got the PhD in the 2009 at the UC Berkeley, and worked as a postdoc at Princeton. He got the Einstein Fellowship and the Spitzer Fellowship, and he was also got the he joined the faculty in the Columbia University in 2013, right? And then he also got the Alfred Strong Fellowship, and now that he got tenure, and that's just last year. So today he's going to talk about the mass messenger picture of the binary variable.
Thank you, Coda. It's a pleasure to be here. The last time I was here, I was actually talking about the same thing in the astronomy department, and at that time it probably seemed like sort of wishful thinking that we would one day have electromagnetic radiation from binary from a source where we also detected the gravitational waves. So I think this has been a really exciting, since its discovery in August, it's been a really exciting time for our field. It really brings together rather disparate areas of physics. We have astrophysicists, we have gravitational wave physicists, we have nuclear physicists, and they sort of are all coming together to understand these events. And sort of the thing I want to emphasize today is that this kilonova emission, which is a thermal glow that's produced by the radioactive decay of heavy elements which are synthesized in the ejecta from these mergers, is important for many reasons. It can tell us where these elements are being produced in the universe, which is a major unsolved mystery. It can also tell us about the conditions during and immediately after the merger, sort of what was going down during the first few seconds after these things coalesced. And then finally, it can also possibly tell us something about the properties of neutron stars more generally, and about the equation of state of dense nuclear matter. So, over the next few years, it's going to be really exciting. And today, I want to try to paint to you a picture of how the different counterparts we saw from this event fit together into one possible picture of what's going down. But we have a lot of work to do yet to really understand even this single event. So I just want to remind everyone what a neutron star is. So this is the remnant core produced when a massive star dies. It evolves to the point where nuclear burning basically stops giving off energy, and the core of the star collapses, and the outer layers explode, and you're left over with this dense object, which is supported largely against gravity by nuclear forces. But there are a number of open questions we have about neutron stars, things that are sort of blunt probes of what's going on in their interiors that as astrophysicists we would like to understand better. One of these is, what is the maximum mass of a neutron star? So this is just showing basically every neutron star with the measured mass, where the mass is given on this axis. And currently, so this is basically how massive a neutron star can be when it's not rotating before it will collapse to a black hole. And we have, maybe one example where we have a well-measured mass of about 2 solar masses. But beyond that, we can't really say. So all we really know is that the maximum mass of a neutron star is greater than about 2 times the mass of the sun. How much greater, we don't really know. Another property of neutron stars we don't know particularly well are what are their radii, which depends on the pressure of the nuclear density material in their outer layers. But for a different equation to state, you assume for the neutron star interior, you can create a plot of the mass of the neutron star versus its radius. But say for a typical 1.4 solar mass neutron star, the radii that are currently allowed by observations are between about 10 and 14 kilometers. And so these are some of the properties of neutron stars we might like to infer from the gravitational waves and their aftermath. So occasionally you can get 2 neutron stars which exist in a binary system. And as you know, if you have a binary, it's essentially a time-dependent quadrupole moment of inertia that causes the radiation of gravitational waves which carry away angular momentum and energy from the system, causing the binary to in-spiral together at an ever-increasing rate. And probably the most, so these systems actually exist in our galaxy. The most famous example is the Taylor pulsar, which was monitored over the last 40 years, and this is sort of the prediction for general relativity for how the orbital period of the binary should shrink as a function of time given some separation A. And this was used to confirm that this approximation, the weak field approximation, is actually quite a good fit to what was observed as the change in the orbital period of the system. These are pulsar systems, so you can very accurately measure the orbital period and see that it's actually decaying. And that particular binary will completely coalesce within about 300 million years. And so we know that these binary neutron stars exist in our own galaxy. We see, several of them. We know that they will merge within the age of the galaxy. So this has always been one of the main targets for LIGO to detect. Now, what LIGO is sensitive to is, of course, the very final several orbits, the final stage of the inspire, the last few minutes or seconds before they actually coalesce, and they're detecting this sort of chirp signal where the gravitational waves are increasing in frequency and amplitude until they finally merge. However, generally the merger itself so far has occurred at frequencies that are actually above those that LIGO is sensitive to. So they see sort of it in-spiraling through their band, and then it sort of merges out of their band at higher frequencies. And that's exactly what they saw in, as I'm sure you heard, on August 17th. They detected the first one of these neutron star binaries. They previously detected several binary black holes, but this was their first neutron star system. And the way they knew it was a neutron star is that the so-called chirp mass, which is a combination of the 2 masses of the neutron stars, a weighted combination that they measured extremely well, was significantly lower than those we would expect if they were black holes. So the particular constraints that they were able to place from the gravitational waves on the individual masses of the system are given here. You can't rule out that these 2 binaries both had exactly the same mass of 1.36 times the mass of the sun, but they could have, they could also have some range. They don't have to be equal. One of them could be 1.6 and the other could be 1.2, for instance. The total mass of the binary measured by LIGO is actually fairly well constrained between 2.74 and 2.8 times the mass of the sun. And what they were able to say originally is that the distance to the source was between about 26 and 48 megaparsecs. This is an astronomer's unit. A parsec is about 3 light years. And so the exciting thing, though, was, so based on just the gravitational waves detected by, so just based on the gravitational waves detected by the 2 LIGO detectors in North America, they were able to place this sort of localize on the sky to this kind of green banana here. They do that primarily by the arrival time delay. So it arrives at one detector and then the other at a slightly later time, and based on triangulating this source on the sky, they can infer that it came from this sort of banana. It so turned out that the Virgo detector, the 3rd gravitational wave instrument, had just come on August 1st. In Italy, and they actually didn't detect this merger, but that was useful information, and they were able to localize the source on the sky to about 30 square degrees, which is really exquisite precision in terms of what they've been able to do in the past. It turns out, I'll come back to this in a second, but it turns out that about within 2 seconds after the gravitational wave chirp had concluded, there was the detection of a very short burst of gamma rays by the Fermi satellite. And that was localized by Fermi to this large blue air region on the sky, which was consistent with the position that LIGO and Virgo had localized the source. And then, as I'll talk about in a second, about 11 hours later, there was the detection of fading optical emission in a galaxy about 40 megaparsecs away, which was consistent with the distance inferred from the gravitational waves. And in fact, there's a degeneracy of the gravitational wave strength between its inclination of the orbital angular momentum with respect to your line of sight and the distance to the source. So a face-on source is a stronger source of gravitational waves. So for a given observed strength, it's farther away, whereas an edge-on source is weaker, so it's closer. By actually measuring the distance to the source through the electromagnetic radiation, we were able to break this degeneracy and infer that this event was viewed within less than about 30 or 4 degrees of the angular momentum vector. So basically, we're viewing it almost, let's say, face-on, or actually almost face-off. But it was actually spiraling into the sky. But it was, we're definitely not observing it edge-on. Okay, that will factor into the story in a second. So this discovery, LIGO detected the merger, disseminated within several hours, the sky position to astronomers, and really, a whole network of telescopes awoke to try to follow up this event over the ensuing days, weeks, and months. And there were many exciting discoveries. So as I just mentioned, the gravitational wave chirp occurred. Within about 2 seconds, there was a burst of gamma rays. This thing happened over the Indian Ocean. Most of the telescopes, the optical telescopes, are in Chile, in the southern hemisphere, so they had to wait for the Earth to rotate. But about 11 hours later, they all got on the source, and there were several groups that discovered a source in this galaxy, as I just mentioned, a few hours later, roughly 11 hours after the event. Not only did we get actual photometry, optical photometry, but we actually took spectra. We were able to get what the light was as a function of the wavelength of the light at different points in time. At early times, within the first few days, there was no detection of the source at X-ray or radio wavelengths. But as we'll talk about in a minute, within about 2 weeks, there was a rising radio source detected at X-ray energies and a rising radio source detected at radio energies. And so taken together, this was basically the largest campaign of electromagnetic follow-up that had ever been conducted on any astronomical event, probably in human history. Each one of these little ticks represents an observation that was taken, and we learned that we have an enormous data set to try to interpret what went into this event. And so my goal over the next 40 minutes or so is to try to go through these different counterparts, the gamma rays, the optical, radio, and X-ray, and sort of tell you what we think, or give you one story for what happened during this event.
Yeah. Bottom center.
Yeah.
Are those temperatures, Planck curves, temperatures?
Yeah, these are like sort of best fit, black body temperatures. Yeah. So it started out, I'll talk about this, it started out very blue in temperature and evolved to become very red. So let me first tell you a little bit about what we think theoretically happens when two neutron stars coalesce. So the outcome is a very sensitive function of two things. One is the total mass of the ingoing binary, and the other is the maximum mass of a neutron star, which, as I told you, is unknown, but it's some value. So if you merge two neutron stars, which have a very large mass relative to the maximum mass, then when they merge, they basically immediately collapse into a black hole within a millisecond or so. That's sort of the dynamical time of the system. We don't think that happened in this event. There were too many fireworks afterwards. We don't think that happened. More likely, you coalesce, if the total mass is a little less, you coalesce into an object which is very rapidly spinning, differentially rotating, peanut-shaped object, which we refer to as a hypermassive neutron star, because it's in a metastable state. It's only stable against gravitational collapse because it's rotating extremely rapidly and it's rotating differentially. But over some period of time, internal viscosity or turbulent viscosity or gravitational waves remove that internal differential rotation, and it loses pressure support and does collapse to a black hole. But that process of collapse sheds a lot of angular momentum and results in the formation of accretion torus surrounding the newly created black hole. But we haven't detected the latter yet. We hope to soon. Okay, so here's a numerical simulation, general relativistic hydrodynamical simulation of two coalescing neutron stars. You're seeing the final few orbits of the merger. Near the end of the in-spiral, you'll start to see the neutron stars exert strong tidal forces on each other. And this can actually result in the loss of mass through the outer Lagrange points and a tidal ejection of material. And then the neutron stars collide together and create this very dense cloud of material surrounding the central peanut that is formed. And that peanut is radiating gravitational waves like crazy until ultimately it collapses into a black hole. There it goes. And because there's so much angular momentum in the initial binary, you end up with this torus of material outside of the horizon at the end. So all of that, was just a matter of milliseconds in real time. So what type of electromagnetic counterpart we get from these events is thought to be a sensitive function of our viewing angle with respect to the angular momentum of the binary. And as I just said, we think for this event, we don't know what this viewing angle was, but we think it's less than about 30 or 40 degrees. So if you happen to be lucky, so the idea is that this accretion disk around the black hole feeds matter into the black hole and possibly powers a relativistic jet of material which comes out in this direction. And dissipation of internal energy in that jet through shocks or magnetic reconnection can accelerate particles which radiate gamma rays. And so if you happen to be within the opening angle of this jet, you might observe a gamma ray burst. But that material is flowing out very relativistically, and so it's relativistically beamed into this direction, into the 1 over gamma cone in this direction. So you think to observe a very bright gamma ray burst, we think you have to be within the opening angle of this jet. But let me say a little bit about that. But this is sort of an outstanding problem. So we've been observing gamma ray bursts for decades. And people have long believed that the so-called short gamma ray bursts might originate from binary neutron star mergers. A lot of this work was the basis of work done partly here from the Swift satellite, which provided a lot of strong evidence that the short gamma ray bursts come from mergers. But there's a lot of open questions as to how these systems might actually produce the relativistic jets we need to get gamma ray bursts. One of the questions is, so what we think is going on is that these neutron stars merge, they form an accretion disk, and one way to create a relativistic jet is if you can generate a very strong magnetic field in the accretion disk, which is able to be pushed up against the horizon of the black hole and extract its spin energy, because the black hole itself is quite rapidly spinning after this process. But in order to get the jet power that we observe, in order to get enough Poynting flux coming out of this jet to explain the observations, the magnetic field has to be amplified quite enormously. Maybe the initial magnetic field of the neutron star is 10 to the 12 gauss, but this violent process of the merger has to amplify the field up to 10 to the 15 gauss or so, and to produce a coherent, ordered structure to the field. So this is sort of an open question. We don't know really how this works. It'd be nice to understand it better. We'd like to know, even if we create a jet, exactly how is its energy being dissipated and producing the gamma ray emission we observe. And we'd also like to know something about what the structure of these jets are. If we're looking down the barrel of the jet, we might see one thing, but maybe if we're looking off at some angle like this, we will see something different. So as I mentioned earlier, this gravitational wave event was accompanied by a burst of gamma rays. So this shows you the gravitational wave chirp. This is gravitational wave frequency versus time, and you could just see whoop, the neutron stars merged right at that point. And then there was about 1.7 seconds of nothing. And then the Fermi and integral satellites detected a burst of gamma rays, which lasted for about a second after that point. And so there's a number of questions here, like why are the gamma rays delayed relative to the merger? I would naively think maybe they would merge, a black hole would form very quickly, I would make a jet, and it would immediately produce gamma rays. So there's a bit of a question here as to why there is this delay. Maybe did it take a while for the black hole to form after the merger? Maybe the black hole formed immediately, but it took a while to create this jet. Maybe the jet has to go out very far to dissipate its energy, and it took some extra time to come to our line of sight relative to the direct path taken by the gravitational waves. So I think this is the kind of questions we're still grappling with. This GRB was usual in the way that it looked spectrally, but was very unusual in the sense that given how close it occurred, it was actually intrinsically much less luminous than the gamma ray bursts we know about before at cosmological distances, by at least a factor of 100, if not 10,000. And again, we don't quite know why this is the case, but it's likely related to the fact that we were not observing this event directly down the barrel of the jet, but off at some angle, possibly up to 0.5 or 0.6 steradians. And somehow, if you observe one of these jets off axis, it's significantly less luminous. Okay. We also have other evidence that we observed this event slightly off of the jet axis. This comes in terms of the X-ray and radio emission, which, as I mentioned, was observed only about a few weeks after the event. So this just shows the luminosity, if you will, or the flux as a function of time. And there was no detection of X-rays within a few days after the merger. There was, there were some upper limits in terms of the radio emission. But then essentially about 2 weeks later, we saw this rising X-ray and radio emission, which is consistent with synchrotron radiation this entire time. And so what we think this is produced by is the interaction of the relativistic jet that was producing the gamma ray burst, say, with the interstellar medium surrounding the merger site. Okay, so there's gas pervading space. If you eject a relativistic material into space, it will produce a shock wave as it slows down. This is what Peter Mazzaros predicted 20 years ago. And this will produce through X-ray radio synchrotron radiation. But normally in a gamma ray burst, you see it immediately. You see the gamma ray burst, and then immediately it's brighten the X-rays and radio. In this event, we had to wait for about 2 weeks for it to brighten. And again, we think this is related to the fact that we weren't within the 1/gamma cone of the jet. It was initially, this blast wave was initially producing this radiation, but it was beamed in this direction out of our line of sight, but only after it slows. For instance, if it slows down as it interacts with the interstellar medium, then that 1/gamma cone into which it's beamed will widen and enter our line of sight. More likely, what we think is happening in this event is that the jet has some angular structure. So instead of this core of the jet, there's actually some wings of the jet which are slightly less relativistic, and they take a little longer to transfer their energy to the interstellar medium, and so there's a delay in terms of the rising X-ray and radio emission. But this is full, as far as we can tell right now, the data is consistent with there have been a successful GRB off of our line of sight, and we're basically seeing seeing this slightly from the side. But that's not, we haven't proven that this event would have looked like a normal cosmological GRB on axis, but in my opinion, it's consistent with that picture right now. Okay, but let me get to the main point of my talk, which is this kilonova. So this GRB, its afterglow, all the stuff I was just talking about comes from the fastest parts of the ejecta, the ultra-relativistic material. Most of the ejecta from a merger doesn't come out with the speed of light. It comes out at 1/10 or 2/10 the speed of light. And this is this material, as it expands into space, decompresses from very high densities, synthesizes very heavy radioactive elements, which produce a thermal glow known as a kilonova. So the basic point here is that there are several sources of neutron-rich material that are expelled into space during the merger. I showed you the simulation of the two merging neutron stars where you saw this material that was ejected tidally in the equatorial plane of the binary. This matter comes off very neutron-rich. It's essentially just taking neutron star guts and throwing them into space directly. You can also, when the neutron stars collide, they produce a shock wave between them, which produces a very high pressure region, which tends to squeeze material out of the polar direction, kind of like squeezing a tube of toothpaste. So we call that the collisional ejecta. That material is strongly irradiated by neutrinos, which can turn neutrons back into protons. It's also heated to high temperatures, and as a result, it doesn't tend to be quite as neutron rich as this tidal material. Maybe the neutron to proton ratio is a few as opposed to 10. This material that we call dynamical because it comes out during the merger itself on a matter of milliseconds or so. You're right in the immediate aftermath of the explosion, and it comes out with quite a high velocity. There's a second part of the ejecta which comes out later, and these are outflows from this accretion disk. The same accretion disk which is feeding the gamma ray burst jet also produces outflows from its surface. I think you may have even heard a talk on this by Daniel Siegel here a few weeks ago. He's done really excellent numerical work on studying these accretion disks. And it turns out that black holes are somewhat fussy eaters. You put an accretion disk around them and not all of it gets into the hole. A large fraction of it is expelled in a wind. And in fact, this can be a sizable amount of the torus. And in fact, maybe if you have a tenth of the solar mass in the accretion disk, which is a typical value, you can eject in the wind several hundreds of the solar mass through this accretion disk outflow. But that comes out somewhat later in time as the disk is consumed. It could take up to a second or so. And it tends to come out with a somewhat lower velocity than the dynamical ejecta. So the point is, you collide two neutron stars together, there's a lot of neutron-rich stuff that's ejected into space. Oh, here's this is actually Daniel's simulation, the first GRMHP simulations of this post-merger accretion disk, which include all of the relevant nuclear physics and neutrino physics. And I'll just show you the simulation. So this is just showing you that, as matter accretes onto the black hole, you get turbulence driven by the magnetorotational instability. You blow outflows from the disk. There's very interesting physics which goes into what controls the composition of these outflows. The disks are electron degenerate, and this tends to drive the composition in the midplane to be very neutron rich and to feed very neutron rich outflows. And what we find is that about 40% of the initial torus will eventually be expelled into space, and that this can be a very important source of mass ejection in these systems. So this matter is expanding from the accretion disk. These are a bunch of test particles into space. This is just thousands of test trajectories. We're following a given fluid element as it flies to infinity. And as matter decompresses from these nuclear densities, it will create very heavy elements through what we call rapid neutron capture nucleosynthesis, or the R process. So essentially, basically what happens is you start off with free neutrons and protons in the disk, which is very hot. As it expands, all of the protons get together with some of the neutrons through standard thermonuclear reactions to form these heavy seed nuclei. But there are so many neutrons left over that the only way they get incorporated into the nuclei is through subsequent neutron captures. And you capture neutrons at a rate which is much faster than they're able to beta decay back to stability. So you temporarily create a bunch of very neutron-rich nuclei and can produce the heaviest elements this way. So here's an example of an R process network. This is proton number, this is neutron number. These are the color shows you the abundances. This is the stable value up here. We're following a single fluid element as it decompresses from high densities and temperatures, so these will drop as a function of time. And at the top you can see the abundances as a function of atomic mass number. And we're starting off at t equals 0, and then we'll let it run. So what happens is you capture neutrons, which moves you this way, and then you undergo beta decays, which moves you this way. You capture more neutrons, beta decays, neutrons. And this is the way you go and form the heaviest elements in the universe. So we're capturing neutrons, matter's decompressing. About a second or so afterwards, we run out of neutrons to capture. And then slowly everything decays back over minutes, hours, days, months, years, millions of years. We form an abundance distribution of these heavy elements. So this is just a particular example for, again, one fluid element. This is abundance versus atomic mass number. This is a particularly neutron-rich fluid element. And what you can do is you can basically produce, this is the so-called second R process peak near xenon and silver, the third R process peak near platinum and gold. You can even produce the heaviest elements, uranium, the transuranic elements, uranium and thorium. And these types of calculations show that you can produce the qualitative features of the solar system abundances. But the details really depend, to be able to translate our models into theoretical predictions for, say, the abundances in our own solar system, would require understanding all of the properties of the nuclei off of the value of stability here. Neutron capture cross-sections, masses, a lot of things we haven't measured yet, but may be measured in the future, for instance, by effort. Okay, so, but the main point for my talk is that this matter, these isotopes you create are highly unstable. So as you eject them into space, they will slowly decay back to stable elements. And this is crucial because if the matter wasn't being heated by radioactivity, it would expand adiabatically and get extremely cold, and we would never be able to see it from these distances. But the radioactivity keeps the material hot. So this is the radioactive power, ergs per gram per second, versus time after the merger. If I just have a single decaying nucleus, it would have a constant radioactive heating followed by an exponential decay. But here I have hundreds of nuclei. So I have ones that have a half-life of a minute, that decays to a half-life of an hour, that decays to a half-life of a day. And when you add together their total radioactive heating, it's actually more like a power law in time. And it's a combination of beta decays, alpha decays, fissioning. And that alone isn't enough to produce this emission. What you're producing is a bunch of radioactive particles, energetic, beta decay electrons, fission fragments. But they have to share their energy through the plasma via Coulomb collisions, and they do so actually pretty effectively at these early times. And so what we did in 2010 is we were basically the first to calculate this radioactive heating, which is crucial because it takes about a day for the ejector to become transparent to where this heat can escape to the observer. And so what's crucial for this calculation is what the radioactive heating is doing a day or so after the merger. So as I mentioned, the material you eject is initially highly opaque. So even if you're releasing an enormous amount of energy, none of it's going to escape because the photons are trapped. But if you wait about a day or so, the photons can start to diffuse out of this expanding ejected cloud. And that produces emission. So these are the first calculations we did of this with the correct nuclear heating, showing the luminosity versus time. And what we found is if I eject 1/100th of a solar mass at a 10th the speed of light into space, it will produce a transient that is about 3 by 10 to the 41 ergs per second in its luminosity, and will last for about a day before decaying subsequently. And this was about 1,000 times brighter than things we refer to as classical nova in our own galaxy. So we called these events kilonova in this work. And so after this discovery of LIGO's neutron star merger, the data was coming in. I, with some help, concatenated or put together a bolometric light curve for this event. And I simply overplot the very first figure from our paper, this black line, now shown as red, over the data points, which is shown as blue. And it was really an absolutely amazing fit. So this was quite a religious experience for me. But I guess what I want to say is that there was so this alone, so we were able to fit the bolometric data quite well, but you notice some things that don't agree. Well, one thing is so you notice, for instance, our original models predicted this bump out here, which isn't seen in the data. And that's because we didn't know what to assume. I'll come back to this. We didn't know what to assume for the opacity of the material, how easy it is for photons to escape. In these early calculations, this is purely exotic nuclei. We had no idea what to assume for the opacity. So we assumed iron opacity, which turns out to be an okay approximation at early times. But iron has a well-defined ionization transition at a few thousand Kelvin, and it causes a sudden change in opacity and produces a bump. The observed light curve doesn't show such a bump, and it's not surprising because it's not actually made of iron. We were just using that as a proxy for the opacity. But anyways, I'll come back to that in a second. So,
Brian, you said that for a day or so, one does not see anything, right? For a day or so. This is it.
So this is 11 hours. That was the first observation anyone got on. We have no idea what was going on before that. So this was the 11 hours it took for the Earth to rotate. So it got dark and chilly. So we don't know what was happening before that. In fact, now that's one of the hot areas, is to figure out how brighter or dimmer this should be at the first hours, because that's going to tell us. By this time, the ejecta sort of forgot where it came from. But at early times, it may have some imprint of how it was ejected, and that's something we would like to be able to detect in the future. If we can, if LIGO can give earlier alerts and astronomers have telescopes well positioned across the globe, we should be able to do this. Okay, so this event evolved from being very blue at early times to being very red at late times, more so than these original models predicted. So let me show you some specific spectral evolution. So this just shows you, this is the spectra at different points in time. 1.5 days after the merger, 2.5, 3.5, 4.5, 7.5, 9.5. This is in the optical band from 4,000 to 18,000 angstroms. This goes a bit further into the infrared by a different group. And what you see is at very early times, the spectrum is featureless but very blue. And it's featureless because it's expanding very fast, about 3/10 the speed of light. So all of any spectral features lined would be Doppler broadened away. But as time goes on, you see deeper into the ejecta where the velocity is getting a little bit lower, more like 1/10 the speed of light. And you can start to see spectral features emerge. There's some sort of broad absorption feature that appears here in the near infrared. There's some sort of undulations here. So I'll come back to this, but the truth of the matter is we don't actually know which elements are producing these specific absorption features that we see, but they're unlike any absorption features that have ever been seen in an astrophysical explosion before, which probably means they're coming from some of these heaviest elements. And in fact, we're now beginning to appreciate the fact that which elements you have in the ejecta very sensitively control the colors of this kilonova emission. And it comes down to the periodic table. The second R process elements, up to the second R process peak, are mostly deep elements that have D shell valence. So photons diffuse out of the ejecta. The dominant source of opacity that's trapping the photons is a forest of absorption lines produced by the atomic nuclei, the atoms in the ejecta. And so exactly how complex those atoms are affects how easily radiation is able to diffuse out. If you just have the lighter R process elements up to the second peak, you mostly have fairly simple atomic structures like the D shell, like iron is a fairly simple, even though it's a million lines. It's actually, for these purposes, a fairly simple atom. However, if you go up and produce the third R process peak, the very heaviest elements in the universe, you also produce some of these lanthanide nuclei. And remember, they're supposed to fit in here. They don't. And they have more complex F-shell valence electron structure. An electron has many more transitions in one of these half-filled lanthanide nuclei than it does in iron. It has many more lines. And those lines completely blanket out the optical and UV. So if you have lanthanides in your ejecta, so if you don't have lanthanides, if you just have iron or light R process nuclei, then our original predictions, these blue kilonova, is actually a good approximation. So the radiation comes out very blue, it peaks at about 1 day. Iron is an okay approximation of the opacity. However, if you also have a substantial fraction of lanthanide nuclei in your ejecta, those F-shell valence electrons will trap the UV, block the UV and optical radiation, and the emission will actually come out in the infrared. And the ejecta has to expand a bit further for the radiation to get out. So instead of peaking about a day, it will actually last about a week. Okay. And the key point is whether we get something that is blue and fast evolving or red and slow evolving depends on whether there are lanthanides in the ejecta. And whether there are lanthanides depends on how neutron-rich the ejected material was. If it's fairly proton-rich, you'll just produce the light R process elements. But if you have enough neutrons to capture your way up to the lanthanide, you will also produce these heavy elements. And we think we saw in this event both. I'll come back to that in a second. And in fact, we have theoretical reasons that we could see both. So if you're an observer up here, there's a neutron star merger. The matter that comes out when the neutron stars slam together in the polar direction, that tends to be fairly neutron poor and will produce just these light arc process elements. And that will produce a blue cloud of material which produces a blue kilonova. But you're also going to have outflows that come out later from the accretion disk or from the tidal tails of the merger, and they are going to be more neutron rich. They will synthesize also the heavy elements and can produce a second component to the ejecta. Okay, so depending on your viewing angle, you may actually see both this blue and this red kilonova. I realize this is all very tough stuff, but when we fit the photometric data from this event to one of these blue plus red models, so it starts off very blue and then its spectral peak moves into the near infrared. This is astronomers' units for how bright it was versus time. These are the UV light curves. In the UV and the blue, it just decays away very fast. In the infrared, you get this very long-lived emission that lasts for almost a week. When we fit it to this sort of two-component model, the blue light arc process nuclei and red arc process nuclei, heavy arc process nuclei, we found that about 2 by 10 to the minus 2 solar masses of the blue stuff expanding at about 0.3 C, and about 3 times as much of the red stuff expanding at about 0.1 C. Okay. That provides our best fit model to the data. So we do think that we have evidence in this event that we created both light and heavy arc process nuclei. And this is an old mystery going back to Burbage, Toyle, and Fowler and Al Cameron in the 1950s. They knew that the arc process must happen in nature, but there was no explanation for where it happened in nature. There's been no direct evidence of the arc process at any place that we observed before. And now we think we have pretty good evidence that the mergers at least are an important, if not dominant, source for these elements in the universe. And the argument goes something like as follows. The rate at which you'd have to inject our process nuclei into our galaxy before the formation of the solar system per year in order to explain the abundances on Earth is this rate per year. We now have a rate of binary neutron star mergers in the galaxy thanks to LIGO. It's uncertain by about an order of magnitude since we only have one event, but we do have a rate. And so we can calculate what is the minimum amount of our process material that would need to be produced per merger if we wanted to explain their abundances on Earth. And that number is between a few thousandths and a few hundredths of a solar mass per merger. And now we have an event where our best fit models tell us that at least 5 by 10 to the minus 2 solar masses was produced in this event. Which, even if the LIGO rate ends up being on the low end, is sufficient to produce the solar system abundances. So we basically think we found the site of gold in the universe. And this particular event produced about 10 Earth masses of gold. So pretty impressive yield if we could figure out how to fly there in mind. Okay. All right, I have about 10 minutes or so left, maybe. So I'm going to tell you a little bit about what we can learn from this event about the equations. Actually, maybe I'm just going to shoot ahead. I think I'm going to skip over equation of state constraints unless people are really interested. Maybe I'll come back. But I guess the main point I want to make is that well, let me make the point pretty quickly. So I'm not going to say much about what LIGO did actually place a constraint on the radii of neutron stars by not detecting the losses of gravitational wave phase due to tidal interactions. I realize it's a loaded statement. They were able to put an upper limit on the radii of neutron stars. I'm not going to talk too much about that. I will simply say, though, that the basic idea is that we have 4 possible outcomes from one of these mergers. We could either immediately collapse into a black hole. We could possibly produce, in the other end, if the mass of the... So basically what it comes down to is what is the maximum mass of the neutron star, which we don't know, and what is the mass of the 2 neutron stars that merged in this event. So if the total mass of the binary was above between about 30 and 60% of the maximum mass of the neutron star, we think it would have immediately collapsed into a black hole. We didn't observe that. Likewise, if the total mass was less than about 20% of the maximum mass, we think we would have produced a long-lived neutron star, one that didn't collapse into a black hole. And we don't think that happened either. So the basic point is that by demanding that this event form one of these temporarily stable hypermassive neutron stars, we could actually put an upper limit on the maximum mass of the neutron star. Yeah, so the basic point is that if we had formed a stable neutron star in this event, it would likely be characterized by two properties. One is it definitely would be spinning very, very rapidly with a rotation period of about a millisecond just by angular momentum conservation. And it would have an enormous rotational energy between about 10 to the 52 and 10 to the 53 ergs. It would also very likely have a strong magnetic field because there's an enormous amount of shear energy liberated when these two neutron stars coalesce. And magnetic fields tend to be frozen into conductors like neutron stars, and that shearing winds up and amplifies the magnetic field. And in simulations by Kenta Gucci in the audience here have shown that the magnetic field can be amplified to 10 to the 15 or even 10 to the 16 Gauss in these remnants. So if you produce a neutron star with 10 to the 15 Gauss and a millisecond rotation period, it has an enormous rotational energy, you're going to notice it. Okay? It's going to spin down through its dipole radiation and eject an enormous amount of energy into its environment of order this amount of energy. And we see no evidence for that in this event. We've modeled this, we think we know what this might look like. We don't see, we can count up the energy in the gamma ray burst jet and in the kilonova ejecta, and it doesn't add up to 10 to the 52 ergs. So we think that we can rule out a stable remnant in this event. So we're pigeonholing ourselves into one of these hypermassive neutron star remnants, which allows us to put an upper limit on the maximum mass. So very quickly, I showed you at the beginning of this talk, mass versus radius for neutron stars. We don't know the maximum mass, which is where these equations of state terminate up here. We don't know the radii of neutron stars. Due to this one event, we're starting to constrain this potentially. So I didn't have time to discuss it by the fact that we didn't see the black hole didn't see a prompt collapse. We could actually put a lower limit on the radius of the neutron star. LIGO didn't detect tidal effects, which puts an upper limit. And then we think we have a constraint on the maximum mass because this thing didn't survive very long. And so there's actually a limited number of equations of states which survive all of these constraints if we believe all of them. Of course, they all come with their own systematic uncertainties, but the way we will tell is we'll construct a similar diagram for the next neutron star merger, and it better be consistent with the one we constructed for this one. But let me spend a little bit of time talking about, just a few minutes talking about the future. So we now just have one merger, but LIGO is continuing to be upgraded. It's only partly, it's only part of the way on this path to its, its design sensitivity. Once it reaches design sensitivity based on this one event, we can infer that they will detect between roughly one of these every week and one of these every couple months. Okay, so this type of discovery is going to become fairly routine, we hope, within the next few years. So what we like to do is to make predictions for, if we think we understand this event, we like to make predictions for how the next one looks like if we view it at a different angle or if there's different properties of the incoming binary that are coalescing. So one thing is the red ejecta, so the lanthanide rich ejecta, which produces the red kilonova, can block the blue kilonova. It has a much higher optical opacity. So for this event, where we were within about 30 degrees of the angular momentum axis, the blue kilonova we might be observable, but it's conceivable that if we view event more equatorial on, that the redder material could actually block it. Okay. So we might see a very different color evolution if we're viewing this event from a different angle. Because the main point is that the composition and geometry of the ejecta is sensitively probed by these kilonova light curves. Generally speaking, the the reason we have this blue kilonova, the reason we have this component of the ejecta that is relatively neutron poor, is because we think that part of the ejecta was strongly irradiated by neutrinos from the neutron star remnant. So the longer the neutron star survives after the merger, the more it will be able to irradiate its environment, and the bluer the kilonova will be, we think. The longer the remnant will survive depends on how massive it is. A lower mass binary will live longer than a higher mass one. So we should expect that if we have a smaller binary mass inferred from LIGO, that will give us a longer lifetime, and we'll have a brighter blue component to the kilonova than the red one. This is a prediction I'm willing to make. So if we have a high mass, we will collapse right away, and most of the emission will be very neutron rich. But if it survives longer, we have a long-lived neutron star, it could produce most of the blue emission. And maybe we will even see one of these millisecond magnetars that produces something qualitatively different. I don't want to spend any time talking about that, unfortunately, because I want to finish up. But so the main thing is I just want to say that, to me, this was actually a fairly well-behaved merger, by which I mean most of the things that we saw were either seen before in some way observationally or were theoretically predicted. So the sequence of events, as far as one possible sequence of events, is I have my two neutron stars that merge, okay? They collide together. There's a very strong shock wave between them, okay? It drives a plume of highly neutrino-irradiated material into the polar direction. Okay? This material is irradiated by neutrinos. It's fairly neutron poor. It only produces the light R process elements. But it nevertheless produces, over the course of a day, nevertheless produces this blue radiation that you saw. I then collapse very quickly, or I form a temporarily stable hypermassive neutron star that maybe survives for 100 milliseconds. It collapses into a black hole. That black hole has an accretion disk around it. That accretion disk powers a relativistic jet, which breaks through this blue kilonova ejecta and produces the gamma rays that we observed 2 seconds after the merger. It also produces X-ray and radio emission as that material runs into the interstellar medium. The accretion disk, in addition to powering the jet, produces a wind of mildly relativistic material, which I think Dan Siegel talked about here, is fairly neutron rich and will produce also these heavier R process elements, which powered most of the infrared emission that we saw coming out over the ensuing week or so. Again, you can believe my story, but I think the way we're going, or not, but I think the way we're going to test it going ahead is to see how all of these properties vary as we see different things going in, as we see these things from different angles, and we see different masses of the ingoing original binary to really test our prediction. So I think this is exciting because it tells us for the first time where the heaviest elements in the universe come from. It gives us a bright beacon to these gravitational wave sources. This kilonova was bright. 17th magnitude at 40 megaparsecs means that LSST, the next major wide-field ground-based telescope, could detect these kilonova to gigaparsec distances. So I didn't even have a chance to talk about it, but you can use these mergers as possible standard sirens to do cosmology, so maybe we should be thinking about these kilonova as a way to locate the galaxies to these sources in their redshift for a large sample of these things. And so I think it's going to be a really exciting time over the next 3 or 4 years as we see more of these mergers and are able to test some of these ideas. I'll finish there. Thank you.
It's time for questions.
Why is Neutron star a conductor?
Why is it a good conductor? Oh, well, it has a lot of, there are a lot of electrons in it. That's one reason. It can also be superconducting inside. But neutron star is not entirely neutrons. There are protons in it, so there are electrons. So yeah, so they freely move in. It's a plasma. And then also, yeah, the degeneracy is full, so the electrons have long mean free paths.
So from GW17 and A17, we know that two neutron star modules can cause short gamma bursts, right?
We don't, or we do know?
We do know.
Yeah. So I agree with you. The burst that we saw had, in many ways looked like other short gamma ray bursts we've seen before. The one quibble is that it was very low luminosity relative to bursts that we've seen. That's probably because we were doing it off of the jet axis. But yeah.
So what's our understanding of the short gamma ray bursts now? Can we see that most of the short gamma ray bursts are caused by the neutron star module? Can we see that?
I don't think we can say that at this time. Everything is consistent with that. But until we know better what the beaming correction is, we can't really directly compare the rates. So I'd say that's my belief is that they all are, but I don't think we can prove that yet.
Yeah. When you showed us the radiation spectrum, as it went from blue to red, I mean there was these two constant blank spots at around 9,000 angstroms and I think 14,000.
Yeah.
Why is that the case? I mean, it's throughout the time. It's
those are. You don't believe those. Those. There's some atmospheric. Maybe some. We were talking about this earlier. The observers know what this is. Maybe is this like the place in the atmosphere where there's a lot of absorption or something? Anyone observing knows. So I think that there are certain. So those are certain parts of the spectrum which are. There's some. I think it's atmospheric absorption, but I could be wrong. Not true. It's true. Okay. So yeah. So don't trust anything in those little gray regions.
Do the simulations give any idea about what the opening angle of the blue component would be?
It's quite wide, but it's of order 40 or 50 degrees in terms of its width. The shock-heated ejecta, it tends to be over on the whole spherically symmetric, but the part that has the highest electron fraction, sort of, 40 or 50 degrees. So not as collimated as a GRB. And also, since it's not expanding, I mean, it's expanding at 0.2 or 0.3 C, so relativistic effects are pretty minor.
So for this follow-up question, do you think that the opening angle will be the same even if the blue component is produced by the outflows from neutron stars?
Yeah, so I didn't talk about it, but I'm a little uncomfortable with how high an ejective mass from this is. So it may be that the post-merger neutron star could also produce an outflow.
Okay, it's similar.
But it's a similar thing. It's probably similar. It's probably, I would guess that, it's concentrated more equatorially, but there's usually a disk or something blocking it. So let's say 60 degrees, something like that.
So does the observation of R process elements in this event rule out any other possible sources of R process elements?
No, I think all we could say is that given the large error bars, this event produces enough to explain the solar system abundances. But I don't think we can rule out other possible subdominant contributions. Or even, maybe it will turn out that this was an anomalous event, and the next event, it ejects hardly any material, and the rate is on the low end. So I would be uncomfortable saying we've proven that this is the dominant site. It's clearly a very important site, and but the other major site that people talk about are supernova, core collapse supernova, and I think we have a lot of evidence now that the majority of core collapse supernova, your average garden variety supernova, doesn't produce the R process. I could go into it, but I think we have a lot of theoretical and observational evidence. What people talk about as alternative sites are exotic types of supernova, so like the types of supernova that make gamma ray bursts, long gamma ray bursts, very rapidly spinning stars that make strongly magnetized neutron stars. So those models, theoretically, they sort of work, but observationally, we don't have much of a handle yet. So maybe wait a bit more before we can claim complete victory.
I was rather surprised that we actually discovered electromagnetic counterparts to the first binary neutron star collision. given the beating angles that we expect, I thought that must be an amazing stroke of luck. But, that may be true for the gamma rays, but do you think, what would you predict our chances of finding optical and infrared afterglows are from these things, from soft active emission?
Yeah, well, okay, so this kilonova emission, just to emphasize it again, this thermal emission is basically roughly isotropic. So we should see that regardless. The afterglow, yeah, right now we are seeing an optical afterglow. Right now HST data point is consistent with being part of the same power law as the X-rays at radium. But it's substantially dimmer than this kilonova if you're more than about twice the opening angle of the jet, the core jet. So let's say the jet had an opening angle of 0.1 radians. Roughly twice that is where the optical afterglow of the GRB jet would exceed this kilonova.
And once you extrapolate from this one case, would you expect to see the kilonova emission for all of them?
For all short GRBs or for
Neutron star.
Yeah. So LIGO at 200 megaparsecs. I mean, this thing was 17 magnitude, so it will still be 21st or 22nd magnitude, even at the largest distance LIGO hopes to detect neutron stars. So if this event is typical, this game is going to be a lot easier at optical frequencies than we thought. Maybe even ZTF to detect these things, even at the edge of the LIGO volume. But that said, I want to emphasize, though, that a lot of these signatures, the amount of blue eject, et cetera, could depend on the lifetime of the neutron star, which if it's much shorter in some events, it could be much dimmer. So I think we have to be a little cautious. We're going to maybe see a spectrum of events. I think some infrared emission is robust. It's hard to not eject some neutron-rich material. The tidal tails. But this bright optical early emission, let's see.
Other questions?
So, in fact, in a general event in which the hypernova is actually formed, is it correct to say that the accretion disk is going to be 5% of the solar mass or something? Is that
yeah, and almost any time you go through one of these hypermassive neutron star phases, you create a pretty massive disk, and according to Daniel's simulations, 40% of that gets ejected. So I think it's hard to avoid, if the hypermassive outcome is the most likely outcome, it's hard to avoid this much, roughly this quantity of ejected.
And then how far is it from the black hole?
How far is the material? So the accretion disk is, really just brush against it. We're talking about, within 30, 40 kilometers, so just a few ISCO radii. It's just barely. That's the most amazing thing about this to me is that the realization that the platinum in my gold band was at one point within a few RG of a black hole right every time. I think, they've said it are coppers, but it's sort of like, material, maybe you said that. Somebody quoted this, basically all the material is flirting with falling into a black hole that breaks up the precious metals.
Other questions?
This is about the 1.7 seconds. Is that, I know you don't have an exact reason as to why that delay is that, but if we were to assume that the hypermassive black hole, that kind of a life, that's how events occur, then is that the lifetime of that hypermassive neutron?
It could be. That's a good hypothesis. I would say before this event, that would seem a bit long to me. But what simulators have found is as they increase the resolution of their simulations, the neutron star lives longer and longer. Most simulations find that it forms a black hole in 10 or 30 milliseconds, but that's partially because they're not accurately resolving the turbulence that redistributes angular momentum. And as they do that better and better, it seems to live longer. So that might be the case. It might have survived for a whole second, surprisingly. But that could also explain why there was so much ejected too. If it survives longer, it has longer to drive material out of the system.
Okay, so I have a question. So the way you say that hypermassive neutron star is preferred, and when you disfigure the supermassive neutron star, I think that this depends on the how we can produce the large scale quantity. For example, if the magnetic may not be dipole, or because we don't know how the large scale quantities are produced, maybe initially, maybe What do you have any comment on that?
Yeah, my comment is if you want to hide that energy, you have to not dump it into the ejecta over the duration of our current observations, because we would see it in some wavelength. And so, in order to not have a spin down time of the neutron star longer than a month or whatever our current observations, the dipole field would have to be less than 10 to 11 Gauss or something, or maybe a few 10 to 11 Gauss, or maybe 10 to the 12. So I agree with you that it's not at all clear that even if I generate 10 to the 16 Gauss fields on small scales, I will have a dipole field which is greater than 10 to the 12. It seems likely. But you're right, there's that assumption. I mean, nobody could rule out the fact that this thing merged and created an object that has no magnetic field and is just sitting there spinning. We can't rule it out. I agree.
Okay, so maybe one final general question. So, you've this beautiful sequence of observations starting with gravitational waves, gamma ray bursts, and then through the electromagnetic spectrum. But now, if you go back and look at earlier events where you didn't know that there was a gravitational wave, but can you go and reanalyze earlier events and learn something new from those?
Yeah, I mean, one example is looking for this blue kilonova in gamma ray bursts. One example, I mean, yes, you can go back, you have a fresh perspective on these different sources. I mean, mostly we're biased, I mean, the gamma ray bursts, we're mostly biased to see things that are, face on where the jet is pointed at us, and they're happening very far away. So it's hard to go back too much because the observations don't go deep enough to see some of these signals. I realize it probably doesn't completely answer your question, but as far as we can tell, our previous observations are, for the most part consistent with being, clones of this event put much further away, viewed from a different angle. I mean, broadly speaking, I don't think we could say, but there are a few cases. There are a few gamma ray bursts where if they had this blue kilonova, we should have seen it, and we don't. So that may be hinting that some of these gamma ray bursts come from the prompt collapse case. Maybe, I don't know, this is just an idea. Or maybe, maybe some of them aren't mergers or something else. So yeah. And another question that's often come up is, well, why didn't you see this, why haven't we discovered these kilonova before without them? And the answer is just, you have a transient which is fading on a timescale of 1 day, which is 100 times rarer than a supernova, and not that much brighter, about the same luminosity. They're hard to find for astronomers unless LIGO tells you point here, look here, right now. But that will change. That will change with LSSD, with ZTF. We may start to detect these kilonova blindly, and then we'll be able to play the game the other way and see if LIGO saw anything at the time there was one of these detectors with.
Okay, great. Thank Brian again.